Good morning. We are about to start our first video lesson on the first official lesson for calculus. Alright, so everything we've done prior to this has been review, and currently we are about to jump into the first kind of idea that's going to help us lead to that first big picture in calculus. So, I guess technically today, it is the first official day, but it's probably stuff that you already know and stuff that you might be comfortable with. So I think it's a good intro day. Okay. Right here in front of you, you have a little warm up. Okay, so you can try this on your own, and this would be something that we would go over in class. Okay, so try it on your own, go over this in class. So let's go ahead and jump to the first actual note slide. All right, so just to kind of do a little review here, to help us lead into an idea, it says sketch the graph of y minus 2 equals 0.5 x plus 4. Now, this right here hopefully looks a little bit familiar to you. Okay, that is the equation of a line, right? And more specifically, it's the equation of a line in point slope form. Okay, honestly, that's the type of equation for a line that we're going to be dealing with most often, because we're able to see that point, we're able to see that slope. Okay, and we can use a point and a slope to help us with a lot of things. All right. For instance, in this case, the point, right, is for the x value. Remember, it's always the opposite side. Is going to be -4, and the y value is going to be +2. Okay, so that's our line that's passing to the point -4, 2, and our slope is going to be this number right here, right? So that's 0.5 or 1/2. Which, remember that all a slope is in terms of like a line is just your change in y. That triangle means change. It's called delta y, or change in y, over change in x, which you're used to seeing it as y2 minus y1 over x2 minus x1. Okay. And I guess I should have written out the generic form for point slope form here. So just kind of have it so you have it. It is y minus y1 equals m times x minus x1. And again, where x1 comma y1 is the point, and m is your slope. Okay. So anyway, let's go ahead and sketch that. And you've probably done lines a whole bunch of times in your life, but we'll just sketch it real fast, make sure we're good. All right, so remember the point that we're starting off at is at -4, 2. So 1, 2, 3, 4, 1, 2. And honestly, from there, all you gotta do is just do the slope with the change in y over the change in x, and that's rise over run, which means we're going up 1 and to the right 2. So my next point would be right here. Up 1, rise 2, so that'll be over 1, or up 1 over 2 will be right here. It's terrible drawn, but there's our line right there. Okay. And the thing about a line is, remember that the rise over the run, that's up 1 over 2. And the special property of the line is that change in slope, or that slope, is always a constant. Another way of saying slope is to say the rate of change is a constant. Okay, so like no matter what point I'm at, no matter what x value I'm at, it's always going to be going up 1 over 2, up 1 over 2. Like the change in my y value as I change in x is always going to be a constant. Okay, so if I ever ask for the slope or the rate of change, that's easy. You just do up over run, rise over run. Okay, so that's sketching a line. Now let's keep that in mind as we sketch a quadratic. Scroll back up. Okay. Now it says to sketch the graph of y equals x squared. Now we talked about that day one with talking about parent functions. So hopefully you kind of have an idea about what a quadratic looks like. Let's sketch it and look at it. It's got the point 0, 0, over 1, up 1, over 2, up 4, -2, or -1, up 1, -2, up, -4. and that shape keeps going, right? All right. So the sketch wasn't too bad. You've done that a bunch of times, but let's kind of go back to this idea of rate of change. Okay, the rate of change, or another way of saying that is the slope. So, what is the slope? Right? Can we find the slope? Can we find the slope? I'm just writing some key questions here, key ideas to kind of help us with later discussions. Um, Now, remember, when we talk about slope, the only time that I'm ever going to use that word is pretty much when I'm talking about like a rate, like when a linear line, like we're talking about over here in this last example. There, you can find the slope. It's just rise over run. Well, is there a rise over run with a quadratic? Can you find the slope of a quadratic? Well, not really, okay? Because there is no, oops, that's supposed to be a C, no constant slope. And if there's no constant slope, then you can't find the slope. You can't find it because it's not going to be consistent. It's constantly changing with a curve. All right? The slope, say, like right here at this point, is not going to be the slope right here at this point. Okay? So, how we kind of account for that and the difference that we kind of do with that, instead of finding just a slope, we find something called the average rate of change. So I'm going to say the average rate of change. Keyword on average. Now, with a line, we are finding the rate of change, and the average rate of change is the rate of change because it's never changing, so it's always the same, right? Here, when we're talking about average, I mean, it's not going to be exact, but it's going to be kind of around that value. All right, we're averaging all of the slopes, if that makes sense. Okay, and you've done this before in the past. You found average rate of change. Pretty much, it's going to be the slope between 2 points. Or another way of saying the slope between 2 points is the same way as saying the slope of the secant line. All right, the slope of the secant line. And remember what a secant line is from way back when. A secant line is just a line that intersects at 2 points in the graph. Okay? So like for instance, if I wanted to know the average rate of change between the point 0, 0 and the point 2, comma, well, that's all. How about right here? 2, comma 4. All right? I don't know that exact slope because it is not exact. It's constantly changing. But what I can do is I can find the average rate of change, which is going to be the slope of that line right there, or what you call the secant line. And you know how to do that. We just talked about it. Delta y over delta x, which is going to be y2 or 4 minus 0 over 2 minus 0, or x minus x, which is just going to be 2. Okay? So the slope of this line here is 2. It's not the slope of this little curved part here. We can't find that, but it is giving me an idea of what the average rate of change is. It's the average rate of change is 2 over that interval. Okay? But what we're going to learn in calculus is I don't want to know the average. I want to know the exact slope at this point. The exact slope at this point, or the exact slope at this point. Okay? Well, we can't just do that by doing y2 over y1, or y2 minus y1 over x2 minus x1, because it's constantly changing. But the idea, the big idea that we're getting here is how are we going to be able to find the slope at an exact point? No longer just an average rate of change, but an exact point. We're going to call that the instantaneous, if I can spell it, instantaneous rate of change. It's no longer an average, it's going to be an exact. It's going to be instantaneously at a point. All right? That's the idea we're going to try to be getting to. So what I want us to just kind of keep in mind now is all we're going to be worried about is the average rate of change, which is a little bit of a review, but it's going to lead to this big idea of finding the instantaneous rate of change. Okay, so just to help us kind of get to this idea, this is going to be later on down the road. Let's practice finding the average rate of change first. Okay, so let's build up to that first, and that'll help us get to this big idea. So, why is this important? Okay, why are we interested in this? All right, and not just doing the average rate of change. Well, with the rate of change, that's living in a perfect world if we have a constant rate of change. But velocity, or another way of saying rate of change, is not constant. We always treated it that way in the past, but now we're going to start trying to take it to a more real-world application. I mean, think about it. I mean, here's time, here's distance. If I'm talking about my rate at which I'm changing my distance, it's not going to be constant. There's going to be curves. There's going to be acceleration and deceleration, going backwards and forward. As I move, it's not always going to be just a constant. I mean, think about when you're driving. You're not just going to be going the exact same rate of change every single time, right? I mean, like, for example, Jake left home at 1 p.m. and got to Mark's house 68 miles away at 3 p.m. What was his rate of change? What are his units? So first of all, if I'm talking about that, I mean, okay, so I'm starting off at time equals 0. I'm going to go, 1 o'clock to 3 o'clock. That's a total of 2 hours. Okay, so there's 2 hours that have passed, and I've gone all the way up to 68 miles, so 0 to 68. But if I go 2 hours, am I going at a constant rate the entire time? If I am, the average rate of change is just going to be 68 miles divided by 2 hours. So what I'm averaging is, what's that, 34 miles per hour. That's the rate at which I'm changing over time. Okay? But again, the idea is that, like, that's an average rate of change. It's not an exact. Okay? We don't know, like, what I'm interested in, velocity is fluid, and a trip is not traveled at a constant rate. This is just not, like, idealistic. I mean, that's just not reasonable. All right? In calculus, we are interested in the instantaneous rate of change. In other words, what is the velocity at, say, 132? Okay, I mean, like, this is a more reasonable idea of what's going on with our guy, was it Mark or John, or whatever his name is? I mean, it's going to be fluid, all right? I mean, he's going to be stopping and going and stopping and going, but I'm going to be curious about, like, hey, what's his rate of change at this exact point here? Okay, like, I want to know the slope right here. Okay, and that's going to be an exact point. Okay, so I'm only going to have one point. I'm not going to be able to do just the slope of a secant line. We're going to talk about how to do this later. That's kind of the big idea. All right. So for now, let's just forget about that average rate of change, the slope of a secant line. We'll do some examples with that, and we'll practice that a little bit later. Okay. So I'm going to do one example with you. I'm going to leave the rest for you to try on your own. They'll already be filled out online, but as far as the video goes, I'll let you just try to do it on your own, and we can answer questions on those in class tomorrow. Okay? All right, it says, suppose a particle moves in a path that can be graphed by the curve f of t equals t squared. And it says, we want to find the rate of change, or how fast it is traveling. That's what a rate of change is how fast at which it's changing its position at time equals 1. Okay? An average rate of change can be found by taking the change in position, which is your change in y, divided by your change in time, which is your change in x. Okay? And we can find the average rate at time equals 1 by finding the rate of change from a time close to time equals 1. Okay, so let's kind of break down what we're talking about here. If I want to find the rate of change at this particular point of time for this particle, well, it's not a line, so I can't give you an exact point, but I'm going to estimate it using an average rate of change. Like what we talked about earlier in warm-up. Like, I found this rate of change right here. Okay? Well, that's going to be an estimate of this rate of change, this instantaneous rate of change right here. Okay? Well, what if I want to find a more accurate representation of that rate of change? Well, what if I found the rate of change of, say, the secant line like between these 2 points? Wouldn't you say that's going to be a little bit better representation than these 2 points? It's a little bit closer to that exact slope, so it's going to be a better approximation. That's what it's saying in this last line here. You can find the average rate, no problem, between 2 points, but choosing points really close to time equals 1 is going to give me a better approximation of the exact and instant slope at that point, or the exact and instant rate of change. So let's kind of look how we do that in a chart right here. Okay. So let's think about it. When I'm finding average rate of change, I'll say average rate of change. Remember, all that is just your change in y over your change in x, or y2 minus y1 over x2 minus x1. Which in this particular case would be like f of, I'll just say f of time minus f of time 2 minus f of time 1 over time 2 minus time 1, just to get a little more application here, because our x values are actually time, and we're inputting them into some function here. Okay, in this case, t squared. All right, I'm gonna go ahead and give you these points just to kind of get us the ball rolling a little bit here. So let's say like the times begins at, say, time equals 0 when we end at time equals 1. Okay, so I'm going from here to here. Well, so let's figure out what that average rate of change is between these 2 points right here. Okay, so that's going to be, and I'll write it this way, I'll say y2 minus y1 over x2 minus x1, just because that's the notation you're used to seeing. All right, okay, here at this point, at time 1, the y value is what? 1, and at 0, it's 0. So in this case, that's going to be y2 minus y1, so 1 minus 0 over 1 minus 0, or 1. And you can even see that by just looking at the graph. That is a slope of the line 1. So the average rate of change between 0 and 1 is 1. Okay. Well, let's choose a point on the other end. So let's say, how about from like 1 to 2? What will be the average rate of change of that? Okay. Well, again, we're going to be starting at the time 1, we're going to be ending at 2, and you can put the y values if you can see it a little bit better that way. That's at 1, 1, and 2, 4. So that would be like 4 minus 1 over 2 minus 1, which would be 3. And you can even see, again, that's up 3 over 1 on the graph. Okay. So the average rate of change between these 2 points is 3, and between these 2 points is 1. So the idea is that this instantaneous rate of change is somewhere in between that. And you probably can already tell that it's going to be exactly in between that. That's not always the case, but we're going to use smaller intervals to kind of guess that. Okay. Let's say, for instance, like, okay, instead of doing like 0 to 1 or 1 to 2, if I'm trying to find the instantaneous rate of change at 1, how about I choose a really close starting time to 1? How about like 0.9? And I'm going to end at 1. Okay? So that's going to be like, if you can do this in your calculator too, but pretty much it's f of 1, all right, minus f of 0.9 over 1 minus 0.9. Which, if you did that in your calculator, it's 1 squared minus 0.9 squared over 1 minus 0.9. I got 1.9. Okay. So what I did is I just found the slope from this point right here to this point here, a really small interval. And you can kind of see that 1.9 is in between 1 and 3. We're getting closer and closer to that instantaneous rate of change at time equals 1. What if I do the other way? What if I start at 1 and end at 1.1? All right. Well, I can do the same thing. I can do f of 1.1 minus f of 1 over 1.1 minus 1, which if you do that in your calculator, 1.1 squared minus 1 squared over 1.1 minus 1, I got 2.1. So if I go on the other side, you can kind of see I'm getting closer and closer in my slope to the exact slope at that point. And I'm sure you're probably already guessing what that slope is going to be. As I get closer and closer with my intervals, it is going to converge to that value too. Okay, so the instantaneous rate of change, and we're going to actually show that using calculus later on down the road, but the equation for the rate of change, all right, we actually already talked about that up here, but for t squared would just be finding that slope right here. But we kind of showed that it's getting closer and closer to the value 2. Okay, so the average rate of change in this case is going to be equal to 2. All right. Now, that's just a guess, okay, because technically all we did was just estimate it. I mean, we could see that it goes 1.9, 2.1. And if you were to choose like a smaller interval, say like 0.99999 to 1, it's going to be pretty much going to be equal to 2. But all we really did there was just come up with a guess, and if the guess happens to be right, we'll show that with calculus later. But again, everything we did today is nothing like crazy new. It's just using slopes and stuff like that, right? So we guessed that it's going to be equal to 2. That's good for us. And now we can write the equation of the tangent line. Okay, so let's talk about what tangent line is real quick, and then I'll be done. Whenever I was finding the slopes of all these lines in the graph up above, I was finding the slopes of the secant line. Now, whenever I'm wanting to find the slope of the tangent line, so right here at 2, the tangent line is only intersecting at that one point. And if it's only intersecting at that one point, a tangent line is not going to be the average rate of change. A tangent line is going to be an instantaneous rate of change. Because it is only finding the slope at that exact point. Okay? Whereas a secant line finds the slope between 2 points, a tangent line is just intersecting the graph at 1 point. So if we are able to find the slope of that, we have found the slope of the instantaneous rate of change. The only issue with finding the slope of this line is we're only given 1 point on it. That's why we have to estimate it by using smaller and smaller intervals of the average rate of change. But we're going to write the equation because we guessed that the tangent line slope was 2. So we're going to say that our point, we're going to use the point, oh, and I said 2. I meant to say we went over to the point 1, time equals 1, sorry. We're going to say our point is at 1 comma 1, and we assumed that the slope was equal to 2 based off our average rate of changes above. And we're going to estimate that the equation line is y minus 1 equals 2 times x minus 1. Okay. So there you have it. Not too terrible, I don't think. We'll discuss this more in detail later in class. I'll kind of summarize it. But this is just kind of get the ball rolling here. And you can see, and we already discussed this, that the closer that x gets to 1, we see that the slope approaches 2. This suggests that the slope of the tangent line that we just discussed is 2 at x equals 1. This is called the instantaneous rate of change because we are finding the slope at an exact point, all right? And the only way to find this like mathematically correct without guessing is using limits, and that's what the majority of our first unit is going to be about. So we can build up to this idea of finding the instantaneous rate of change. We got to be good at limits first. All right, so we'll lead to that in a little bit. Now, what I want you to try on your own, and we'll discuss later, is try this problem, okay? It's pretty much exactly like the last problem we just did. It's practicing finding the average rate of change, because that's all we know how to do. And then maybe try this problem. This is a little bit more, it's actually doing the same exact thing, but see if you can try this problem. Don't let this notation confuse you right here. All this is saying is we're using the equation y equals the square root of x plus 4 to find our point. So for instance, if x was equal to 5, all right, then the y value would be the square root of 5 plus 4, or 5 comma 3. Okay, so try this problem, try the last problem, and we'll discuss this further, and I will get you the practice problems we'll do in class later. So good job, guys. Good luck. We're going to get the hang of this video thing. Okay. Smile, and we're done.